Let's do quickly this question over here. It says the Venn diagram below has a sample size of 50. First question A is go find the value of X. And so we're going to say, well, all of these things have to add up to 50. So that bit, does that bit, does that bit, does that bit. Okay. You don't have to go use that probability formula about probability of A or B because it's separated already. So you're not overcounting the 8. So you can just say X times X plus 2, put over there, plus 8, plus 4X minus 3, okay, plus 3X minus 7, that's equal to 50. So therefore, X squared plus 2X plus 5 plus 4X plus 3X is plus 7X. Should just on this 8 minus 3 is 5, 5 minus 7 is minus 2, so let's just make it minus 2. Okay, plus 7X minus 50 is equal to 0. So X squared plus 9X minus 52 is equal to 0. You can just use your equation mode of your calculator and it will factorize those to what that can be. X plus 13, X 13 times 0, X minus 4 is equal to 0. So X is minus 13 or X is 4. Don't write time though. It's with a factorize, you just use your equation mode of your calculator. Well, X obviously can't be negative because it's a sample size. So you can't have negative value. So that's not applicable. So X is equal to 4 is your answer. So in this Venn diagram now, this space over here will be 4 times 6, which is equal to 24. Okay, that's A only. This space over here is 8. This space over here will be 4, okay, times 4, which is 16 minus 3, which is 13. And this space over here will be 3 times 4 is 12. 12 minus 7 is 5. It should add up to 50. Let's just do that as a check. 5 and 13 is 18, and 8 is 26, and 24 is 30, 50. Okay, so that's what your Venn diagram. You're really just looking at the red scores now. Okay, then it says calculate the value of the probability of A given that it's not in B. Okay, well, if you just use your formula, okay, that's going to be equal to the probability of A and not B over the probability of not B, or the number. And that's the same thing really, guys. There's a number in A and not B over the number in not B, because the denominator would be the same. So the denominators would cancel. And the numbers that things that are in A and not in B, in A and at the same time not in B, is just basically another way of saying in A only. So that would be 24. And the things not in B are 24 plus 5 is 29. So I get 24 over 29. Yep. Yeah. Which is correct. Okay. Then question B. So see, are events A and B independent? Well, there are 2 tests that you can use for independence. The one that you know from core is that things will be independent if you can show that the probability of A times the probability of B, which I call the theoretical over the actual. So if that's true, then things will be independent. And if they tell you they're independent, you must assume that's true. Okay, that's just independent, misspelt. Okay, but your other thing is this. Your other way you can prove independence is if you've got the probability of A and B. So now that's the proof. If that's true, they're independent. Okay, you know the probability of A given B is probability of A and B over the probability of B. But now, if they're independent, okay, is independent, then the following should happen. Okay, probability of A given B, okay, this is only if they're independent. Well, so with the probability of A given B, but the probability of A and B will now be equal to the probability of A, okay, times the probability of B, if we're assuming they're independent, over the probability of B, and those will cancel. So in other words, if the probability of A given B is equal to the probability of A, in other words, the probability of it being in A is unaffected by B, okay, in other words, they're independent, okay, so that'll be true. This must be true if independent. So there are two tests for independent. Okay, so they're independent. This must be true, and this must be true. So you can use either one of those two things to prove independence for this particular question. Okay. And so it says, are events A and B independent? Okay. Well, we could just go and say, we could use either test. Okay. So we use the first test, this one over here. Okay. Then we're going to say, well, the probability of A times probability of B. Well, the total in A is going to be 24 plus 8, which is 32. So you'd have 32, there's 50 things. The 32 over 50, the things in B, probability of something being in B is this area over here, which is 21 over 50. And if you work that out, 32 over 50 times 21 over 50, you should get an answer. Sorry. So if I go, sorry, I'm checking my calculator, and you go 32 divided by 50 times 21 divided by 50, you get 0.2688. Okay, and if you compare that to the probability of A and B, well, the number of things in A and B is 8. It'll be 8 over 50, which is 16%, which is 0.16. So therefore, they're not equal. The probability of A times probability of B is not equal to the probability of A and B. So therefore, they're not independent. Okay. But the other way you can do it is to use this thing over here, this logic here, that things will be independent if that happens. So we're going to use that. Okay. Well, then we would say, are A and B independent? Justify your answer, Nathan. Probability of A given B must be equal to probability of A. Well, the probability of A, we work that out. Probability of something being in A is 32 over 50. Okay. And the probability of A given B is equal to the probability of A and B. The probability of B, and the probability of A and B from here is 0.16. And the probability of B is equal to 21 over 50. In other words, 0.42. That's 42 over 100. And so here you're going to get probability of A is 0.64. And that one over there is equal to 0.16 divided by 0.42, which is equal to 0.38. So these are not equal, so therefore they can't be independent. Okay. So A and B are not independent events. Okay. Probably easier to use as well, but Right. And then last question. Okay, question 5. So this is a bit of a sneaky one. Okay. And the question says we have the word influence. Okay. So influence. So influence. And this word has got 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. And of those 9 letters, we've got 2 E's. And we've got influence, 2 N's. Okay, 2 E's and 2 N's. Okay. Right, so the question says, find the number of different selections in the, so you're picking 5 letters. Okay. So once you're picking 5 letters from that, you're kind of looking at combinations as opposed to just your normal letter factorial questions. Okay, because you're choosing things. So you've got this pot of 9 letters, and it says we've got to have, we choose 5, we've got to have at least 1 N. And we've got to have, in other words, the number of N's, if you have at least 1 N, and there are 2 N's, either I'm going to have 1 N or 2 N's. Okay. And then I have to have at most 1 E. If I have at most 1 E, it means I've either got no E's or 1 E. But those, I can have any combination of those 2 scenarios. So my options are, well, I could either have 1 N, okay, and no E's. Okay, 1 N and no E's. And if I have 1 N and no E's and I'm choosing 5, okay, so I've got 1 N, no E's, and then I've got to have to choose 4 other things, 4 of the other letters. Okay, now in the scenario, you've got 2 E's, 2 N's, okay, and then you've got 5 other letters. Okay, so you've got 2 E's, 2 N's, 4 plus 5, 5 other letters. So we could either have 1 N, if these criteria to be met, no E's and 4 others. Okay, or I could have this situation where I have 1 N and 1 E. So 1 N, okay, and then 1 E. So I'll have 1 N, but choose 1 N, 1 E, and 3 others. Okay. Or I could have 2 N's and no E's. Okay, in which case I've chosen 2. So I'm going to pick 3 others, 3 other letters. And finally, I could have choose 2 N's, 1 E, chosen 3. I've got to then, if I'm putting 5 overall, I've got to choose 5 others. Right. So in this first scenario, now think of it as you've got 3 different pots. One pot has 2 N's in it, one pot has 2 E's in it, and the other pot has got 5 other letters. Okay. So first of all, okay, what confuses people, you've got to choose 1 N from the pot with 2 N's. Now the number, what are you going to choose? There's no choice. You're going to end up with an N. Okay, it doesn't matter which one you pick because they're identical. That's the key idea. Okay, because they're identical, one N is the same as the other N. Okay, you're going to get an N. Okay, so the number of ways you can get 1 N, choose, you're looking at number of choices, is just 1. Likewise, if you go to the pot of E's, we're not choosing any E's. Okay, so the number of ways you can choose nothing is 1. So your choice is really coming from the fact that you've got to choose 4 others from 5, and order doesn't matter. Okay, so it's a combination. So you're choosing 4 from 5, that's the 4 others. Right, in this scenario over here, but always plus, the number of ways of choosing 1 N, again, as we said before, you're going to get an N. There's no choice. You're going to end up with an N no matter what you do. Okay, 1 N looks the same as the another. So there's one choice for n's. Same thing with e's. You go to the e part, you pull out an e. It's going to be the same. So there's one choice for e. So your choice really is from the, you've got to choose, okay, from the 5 others, you've got to choose 3, right? Then over here, well, if you go into the n part and you're choosing 2 n's, you're always going to get the same thing. So the number of ways of choosing 2 n's is 1. No e's is 1. You've got to choose 3 others, so you're going to get 5 from 3. Okay. And lastly, the number of ways of choosing 2 n's is 1. These are identical. So the number of ways, what you're going to get, there's no choice. If they weren't identical, there'd be 2 choices, 2 choose 1. But now they're identical, so there's only 1 choice of e's. Okay. And you've got to choose 2 others. So from the 5 others, you've got to choose 2. So you're really left with 5 choose 4 plus 5 choose 3 plus 5 choose 3 plus 5 choose 2. Okay. And we go work that on a calculator. We should get an answer of 35. Right, that's question 5.